Dear students, let us continue discussing hyperconjugation. This is also called no bond resonance. Okay, because here what happens uh, when as you know, resonance is involvement of movement of electrons. Here the sigma electrons are involved, and when sigma bond is broken between the atoms, there will be no bond between the atoms. So we call it no bond resonance. So which type of sigma electrons are involved here? It is the CH bond of an alkyl group. Now which alkyl group? The alkyl group which is directly attached to a unsaturated system. By unsaturated system we mean double or triple bond, usually a double bond, or to an atom with an unshared p orbital. By unshared p orbital we mean the carbon with sp2 hybridization, where one of the p orbitals is free, not involved in bonding. So usually the carbocations, they have sp2 hybridization, and double bonds also have sp2 hybridization, where the p orbital, one of the p orbitals of carbon, is not involved in bond formation. It is a permanent effect and it stabilizes a system. Okay, so more the number of hyperconjugation structures, more stable will be the species. So let us begin with the example of ethyl carbocation. You see, ethyl, this carbon CH2 carbon is sp2 hybridized and it has a unhybridized p orbital. Okay, now because of this unhybridized p orbital, it satisfies the condition of hyperconjugation, because you see it's in the neighborhood which we call alpha position. Remember, when we say alpha, it is the position with respect to the carbocation. So this carbon is called alpha carbon, and the hydrogens attached out here are called alpha hydrogen. So as many alpha hydrogens will be there, that many hyperconjugation structures will be there. So since we have here 3 alpha hydrogens, we will get 3 structures. Okay. So here what happens, the bond between carbon and hydrogen is broken, and this electron pair which was forming the bond, which was initially formed by the sharing of electron between carbon and hydrogen, now is being pulled by this carbon. Okay, and it will come here. So the electron will be shared not by carbon and hydrogen now, it will be shared between carbon and carbon. And this carbon, as you know, as its octet is not satisfied, it will readily take the electron. So what will happen? This H now will be remaining near the carbon without a bond, and it will carry a positive charge. Why will it carry a positive charge? Because it lost its electron. And a double bond will be forming between the carbocation, which was earlier positively charged, and the alpha carbon. The double bond will be forming. So this is the change after the first structure of hyperconjugation. Now as you know, these hydrogen, all these 3 hydrogens are attached to the same carbon. So any of the hydrogens can get involved in the hyperconjugation. So initially, first structure we have drawn by involving this hydrogen. Next structure we shall draw by involving this hydrogen and keeping this intact. Third structure we'll draw by involving this hydrogen. Let us see one by one. So I hope the first structure is clear. Now you see, we have shown the positive charge on this hydrogen, and this double bond remains same. Third structure is this hydrogen with a positive charge, and the double bond remains same. So you could see here 1, 2 and 3 structures we got, because there were 3 alpha hydrogens. So as you know, this effect stabilizes the system. So the ethyl carbocation gets stabilized. Ethyl carbocation, remember, is a primary carbocation. It gets stabilized by 3 structures. Now let us see if the carbocation is secondary carbocation. So here we can see here, we have taken isopropyl carbocation, which can be written as CH3 twice CH plus, where the carbon is secondary in nature. The carbocation is secondary in nature. So you can see here also this carbon is attached to two CH3 groups. So we call it secondary. And this, there are 3 bonds around this carbon. So this carbon is also sp2 hybridized. So one of the p orbitals is available here also. We haven't shown, but it is there. Okay. Now in its neighborhood we have 2 carbons, and both the carbons are called alpha carbon. And in each of the alpha carbons we have 3 hydrogens. So altogether we have 6 alpha hydrogens. So since there are 6 alpha hydrogens, we shall get 6 hyperconjugation structures. So I am beginning with the left hand side hydrogens. I am beginning with this hydrogen first, then I'll take up this hydrogen, then I'll take up this. You can take any, but don't repeat the structures. Okay. So when I involve the movement of this electron here, this hydrogen develops a positive charge and a double bond is formed here. This CH3 I am not showing as a structural form, I am writing in the condensed form just like that to save time and to make the structure look less clumsy. Then since we have shown this hydrogen, now we will move to the next hydrogen. So here you see we have a H plus and remaining structure remain the same. And then the third structure here. So we are done with the left hand side, all alpha hydrogens. Next we take up the hydrogens on the right hand side. So when hydrogens from here is involved, so this one will go here and a double bond will form here now. So you see the double bond has formed here, not here. And this way we have taken this hydrogen first, then this hydrogen and this hydrogen. So now you can see the secondary carbocation we got 6 structures, whereas in primary carbocation, which was ethyl carbocation, we got only 3 structures. So which structure becomes more stable? You can understand secondary structure, secondary carbocations are more stable, and we can explain it with the help of hyperconjugation. Earlier we have done the series that primary, secondary, tertiary. Tertiary is most stable, followed by secondary, then primary, and weakest is methyl carbocation. So how do you justify the stability of this carbocation? One of the factors is hyperconjugation. Then you see here this I have given you homework as tertiary carbocation, where you have this is the carbon which is attached to 3 methyl groups. All right. And since each of the methyl groups have 3 hydrogens, so you can see there are 9 alpha hydrogens. So you will be getting 9 structures. You can begin with any of the methyl groups. So suppose here I involve this one. Then remember they are separated by double-headed arrow. So we get H, C, H, and this H will remain as a positive charge. Then a double bond will form here. This positive charge will get neutralized. So don't put any positive charge here, and this CH3 and this CH3 remain as such. Then the remaining 3 structures you can draw by involving this one and this one respectively. Okay, so do practice it because it's a very important factor. And the last one we are doing is for propene. Propene is the example where we don't have a positive charge but we have a unsaturation. Okay, so here what happens, you can see this carbon is sp2, this carbon is also sp2, and this carbon is having an alkyl group attached to it. So we have 3 alpha hydrogens here, this is the alpha carbon, so we get 3 structures. And what is the change here? Since there is no positive charge here, when this electron pair comes here, this electron pair will move to this carbon. Remember here all the carbons have their octet satisfied. Okay, so the moment this electron pair comes here, carbon will have 5 bonds around it, which is not allowed. So immediately this bond will break and the carbon will have a negative charge and this hydrogen will develop a positive charge. So this will continue like this with each of the hydrogens. So that is all about hyperconjugation. Thank you. We'll proceed with the hydrocarbons in the next class.